Hi everybody, in this video we're going to talk about a lower bound for sorting algorithms. More or less, how quickly is it possible to do sorting? So all of the sorts we've looked at thus far, selection sort, insertion sort, bubble sort, quick sort, merge sort, they're all what we call comparison sorts. That means they fundamentally work by picking two elements and comparing them and doing that repeatedly until the entire array has been sorted. Now in the middle, of course, we move elements around and so on, but the fundamental element of work is looking at elements of the array two at a time. And so the question then becomes, what is the minimum number of pairs of elements we can compare and be guaranteed to have sorted the array? Okay, let me explain a little more clearly what I mean by a comparison-based sort. So let's take an array here. And now, as we start any sort of sorting algorithm, we hand the sorting algorithm this array, and the algorithm has no idea what's in any of the spots in the array. Right? It hasn't looked yet. And so as it tackles this process of sorting the array, it's going to do a series of comparisons. So let's say we've got a selection sort. The first thing a selection sort's going to do is look in the first two elements and see which one's bigger. And then it will compare the first element and the third element. And the fourth element, right, this is the inner loop as it walks down the array, the fifth element, and the last element. So it goes through and does all these comparisons, and when it's done, the selection sort will take the smallest element and move it to the beginning, and then it will start the next iteration of the outer loop, and it will compare these two, and then these two, and then these two, and so on. So it's doing all of these comparisons, and by the time it's done doing these n-squared comparisons and a couple of swaps along the way, the array is sorted. And so, like I mentioned, the real question here is, if we had the best algorithm possible, how few sorts could we do? And I'm not talking about for a special array where things work out nicely. What kind of guarantee can you make me? Regardless of the array you give me, I can get it sorted in X comparisons. You know, how small can we make this guarantee of X? So the challenge is, how can we analyze or make a statement about all possible algorithms that anybody could ever come up with? These kind of arguments are generally difficult to make. They're some of the more difficult proofs to conceive of and write. Fortunately, this one's not too bad. So let me explain how we can make a claim about how few comparisons are even possible. So let's start with a smaller array. So same idea here. Here's just some array of size 3 that we hand off to a sorting algorithm, any comparison-based sorting algorithm. We, of course, have no idea at the start what's in any of these boxes. And to be able to talk about this, I'll label these boxes A0, A1, and A2. Now, regardless of the sorting algorithm, once we have this set up, we can reframe the sort as a search problem. So once we've sorted this array, we have one of 6 possible results, right? So once we've taken this array and shuffled the boxes around so that they're in increasing order, we've done one of 6 things. After we've peeked in all of these boxes, what we're going to do is we're going to find that the sorted order of the array is one of these 6 choices below. And so what our sorting algorithm is doing is that every time we look inside a pair of boxes, every time we make a comparison, we get to cross out one or more of these possibilities. So let's say, for example, I start out my algorithm, and my algorithm, for whatever reason, decides to look in boxes 0 and 1. And when it looks inside, we find out that there's a 3 in A0 and there's a 2 in A1. So we've done our first comparison. We've compared A0 and A1. We see that A0 is bigger. So when we do that, what that lets us do, cross out all of the possibilities where A0 comes before A1. And then we'll pick another 2 boxes to look at. Let's say we decide to look at A0 and A2, and when we look in A2, we see that there's a 6 in A2. So now we know that A2 comes after A0. So we can cross out the possibility where A2 comes before A0. Here's another possibility where A2 comes before A0. So that means the sorted order of this array would have to be A1, A0, A2, which is the sorted order. So that's our model. Our model of any sorting algorithm is that we're implicitly, in some way, ruling out a possible order of the array every time we take a peek at a pair of boxes. And so now, how many peeks do we need before we're guaranteed to have whittled this down to one possible choice? Once you've got it down to one possible choice, you've sorted the array. So the question is, what's the best we can do? How fast can we cut these down? Okay, so now the question is, what's the best you can possibly do at each step? So here I've reset the diagram, and so we're looking at the very first step of a comparison-based sort. I have an array. I have no idea what's in any of the boxes, and so I somehow have to pick two boxes to look in. And if I do this perfectly and I pick the best possible pair of boxes to look in, not having any idea what's in the array, what's the best I can hope for? And the best I can hope for is to cross off half of the choices. Now remember, since we don't have any idea what's in the array, we don't know which box will be bigger and which box will be smaller. So our ideal situation is to cross off half of them. That way, regardless of which one's bigger, we've eliminated half the choices, right? If that balance isn't 50-50, then sometimes you might eliminate, let's say the balance is 90-10. Well, that's not good, because then half the time you would remove 90% of your choices, which is good, but the other half of the time you'll only remove 10% of the choices, and that's bad. What we want is to minimize how many steps we take regardless of what the actual array looks like. And so to do that, we want to split this in the middle every time. And this is our hypothetical, theoretical, best possible algorithm. All right, so now, if we do that, if we have this magic algorithm that always cuts our choices in half, how many comparisons do we need to make? Well, let's see. The first question is, how many choices are we narrowing down? How many possible orderings of this array are there? So if my array has length n, then my number of possible answers, the number of ways that this array may potentially be sorted, is n factorial, right? That's what the factorial is the number of ways of arranging n things. So if I start out with n factorial possible choices here on the left, and I get rid of half of them each time I do a comparison, then I know it's going to take me approximately log base 2 of n factorial to whittle them down to the one final choice. So my minimum number of comparisons is approximately log base 2 of n factorial. All right, that number doesn't mean a whole lot, right? That gives us a good minimum, but let's put that into context. I'm going to do a little bit of mathematics here. So we want to look at the expression log base 2 of n factorial and try to reorganize this into something that seems a little more familiar. All right, so let's see. What's n factorial? N factorial is by definition n times n minus 1 times n minus 2 times n minus 3, and so on, right? So remember, when we take the write this off to the side, right? If I have the log of a times b is the same as the log of a times the log of b, right? When you multiply numbers, you add the logs. So the log of n factorial, the log of n plus the log of n minus 1 plus the log of n minus 2, and so on. Okay, so let's bound this. Let's give it an upper and lower bound so we can see what this number looks like. certainly each value in this sum here, so we've got log n, log of n minus 1, log of n minus 2, they're all smaller than log n. So I can put a log n here, a log n here, a log n here, and so on. And so what that tells us is since the blue, every element in blue is bigger than the element in black, then I can say that the log of n factorial has to be smaller than n log n. Right, because each term up here is smaller than each term down here. So when we add them all up, then what we get from the actual terms on top has to be smaller than our slightly bigger terms on the bottom. Okay, so it's smaller than n log n. You know, that's good. So we can bound it above. Now let's try to bound it below. So we'll go here, and again we've got... Okay, so now we want to find a lower bound for this expression. So let's come up with something that is smaller than all of these terms. And so what I'm going to do is I'm going to get the log of n divided by 2. And I'm only going to do that for the first half. So for values above n over 2, I'm going to lower bound the expression above by the log of n over 2. And so then what do we get as an approximation? We get over here n times 2, because there's n over 2 terms, and we've made each one log of n over 2. So that's necessarily going to be smaller than this piece right here. And then we'll just keep these other terms as they are. And so what that tells us is we've sandwiched the log of n factorial so that it's smaller than n log n, and it's bigger than n over 2 log n over 2. And so what that tells us is that in the world of big O, where we're throwing out the constants, that lets us say that log of n factorial is, the nerdy term we use here is big theta of n log n. So remember, big O gives us like an upper bound. So it says, okay, we're not any worse than n log n. But when we use a theta instead of a big O, then what we're saying is on top of that, not only are we not any worse than n log n, but we're also not any better than n log n. Okay, so that gives you a rough outline of the proof that the best possible comparison sort is going to have to make approximately n log n comparisons and is not going to do any better. There's no cleverness you can come up with to make a comparison-based sorting algorithm do better than n log n. Now, this isn't a complete formal proof. I left some details out, especially at the end here with a little bit of hand waving, because I think for this particular course, the intuition is more important than the details. Perhaps you'll get into the details in like your data structures or your algorithms course. Okay, so remember, this proof here only applies to comparison-based sorts, which is the algorithms we've looked at already. Later, we'll see some algorithms that are non-comparison-based sorts that run faster. What you'll see is they don't generalize. They only work for integers or only work for strings or whatever data they're designed for, whereas the comparison-based sort will work for anything that has a comparison, like a compare to method or a compare method. So as always, email me if you have any questions, especially with some of the math at the end that I went through quickly, and I will see you in a few days.